So let's start. In the previous class, we were looking at these convex or in general minimization problems subject to a bunch of inequality and equality constraints. And we were trying to understand when it is possible to perhaps solve it in closed form. Right? So in that regard, we formulated what we call the dual problem, which is essentially a maximization problem. So the dual problem is first obtained by computing the Lagrangian, which is just f0 of x plus summation lambda I fi of x plus summation vj hj of x. Right? So this Lagrangian is a linear function of the Lagrange multipliers and takes into account all of the inequality and equality constraints. And the Lagrange dual function is obtained by taking the infimum over all possible x in the domain of all the functions of the Lagrangian. Right? So therefore, we have two different problems. The original constraint optimization problem, which was to minimize some function f0 of x subject to inequality and equality constraints, and that has some optimum value, let's call it p star. Now we can also formulate the dual problem, which is maximization of the Lagrange dual function, subject to the constraint that the lambda vectors are all non-negative. So every component is greater than or equal to 0. And this has some optimum value, let's call it d star. We saw that in general, irrespective of the properties of f0, fi, and hj, as long as there is at least one point which satisfies the constraints, as long as the problem is feasible, we always have weak duality. So d star is always going to be a lower bound for p star. Right? In fact, g of lambda comma v is always less than or equal to p star because g, as we saw, was a concave function. Right? But in some scenarios, we also have this strong duality wherein d star is equal to p star. Right? And there are different conditions, or sufficient conditions for strong duality to hold. We'll see some of them, but maybe not all of them. And it won't be possible to go through the proofs of all of these in this particular course. But as long as you have strong duality, it becomes relatively easier to solve the problem, particularly in closed form. So if you solved sort of optimization problems using Lagrange multipliers before, effectively what we were doing was using strong duality without knowing that. Right? So to obtain the optimum value, what you would do is, so the optimum value can be expressed as a supremum over all possible lambda greater than or equal to 0 over all possible v in Rk of the infimum of the Lagrangian. Right? So to solve the problem in closed form, if L were a convex optimization problem, see if f0 were convex, then this basically amounts to finding the saddle point of the Lagrangian. And to solve for p star or d star, all you need to do is find the stationary point of L of x lambda v. So typically in problems where you can solve this in closed form, you generally have only one saddle point, which implies that there's only one stationary point to the Lagrangian. And if you can find that, effectively you solved your problem. You find the stationary point, substitute into L, and you get p star or d star equivalent. Right? So in this class, we'll explore some more problems of convex optimization and see how to solve them. But we'll also analyze some properties of the dual. Right? So recall that there were two sort of dual functions that we've seen so far. One is the Lagrange dual, and the other is the conjugate dual or the Legendre-Fenchel dual of a function. Right? And in the previous class, we saw that if the function is convex, so if you have a convex optimization problem with linear constraints, then the dual function can be expressed as the conjugate of some other function. And in fact, this property can be generalized even further, right? So let's suppose we have a general optimization problem, a minimization problem. Right, so we want to minimize some f of x subject to x satisfying some constraints. Right, so let's assume that the set of constraints forms a convex set, and the function that we're trying to minimize is a convex function. So we assume that f is convex and k is also convex. Right, so this is a constrained convex optimization problem. Now we can convert this into an unconstrained convex optimization problem. And how do we do that? So this is the same as minimizing f of x plus what I call the indicator function ik of x. And what is this indicator? How do we define this particular indicator function? I'll say that this indicator function takes the value 0 if x satisfies the constraints, and it's equal to plus infinity if it does not satisfy the constraint. Is this a convex function? Is this convex? Are you all convinced that this is a convex function? Take any 2 points. If both the points lie inside the convex set, then obviously any point on the line joining those also lies in the convex set, and it takes the value 0 everywhere. Even if one of the points lies outside the convex set, then basically the function value is infinite. So f of alpha x1 plus 1 minus alpha x2 is always infinite. And alpha times f of x, sorry, irrespective of what x. Okay, so let me put it this way. So you take any x1, x2, and alpha. If x1 is not in the convex set or x2 is not in the convex set, we have f of alpha x1 plus 1 minus alpha x2. On the other side, we have alpha times f of x1 plus 1 minus alpha times f of x2. The right hand side is always infinite. So irrespective of what the left hand side is, this inequality is always satisfied. Right? So this is a convex function. F of x is a convex function by assumption. What about the sum of two convex functions? It's guaranteed to be convex. So this is again an unconstrained minimization problem of a convex function. All right, so let's construct the Lagrange dual for
this function will only be convex if k is convex.
Yes, exactly. So both these assumptions are important, that k is convex and f is convex. Okay. Now let's construct the Lagrange dual function. What is it equal to? So L of x comma, there are no constraints at all, right? So what is the Lagrange dual function of this going to be? Itself, right? So I'll reformulate this problem in a slightly different way. Okay, let me call f of x, x1, x2 to be equal to f of x1 plus the indicator function of x2. Okay, I'm introducing a new variable over here. And in fact, I'll generalize this a little further. So suppose that I have an arbitrary function f of x1, x2, which can be expressed as some f1 of x1 plus f2 of a times. All right, I can write this as, suppose I have some function f of x, which can be written as f of x plus f of a times x, where both f1 and f2 are convex. I'll construct, so clearly this is the case over here, right, where A is just the identity matrix. So I can have f1 equal to f and f2 equal to this indicator function. So my ultimate goal is to minimize f of x. It's an unconstrained minimization problem. I'll formulate this as a constrained minimization problem in the following way. So I'll say that f of x1, x2 equal to f1 of x1 plus f2 of x2, but now subject to the constraint that x2 equal to a times x1. This is my original problem. This was the original function that I wanted to minimize. I've just converted this to a constrained minimization. Right? And I'm doing this because I know that I can formulate any constraint optimization problem in this particular form. Okay. Right now it's all mysterious as to why I'm doing this exactly. But now let us look at the Lagrange. x1, x2. I have one equality constraint. So I have just one Lagrange multiplier. This is equal to f1 of x1.
This should be a vector.
Which one? Sorry. Be a vector. f1 of x1 plus f2 of x2 plus v times, let's say, x2 minus a times x1. what is g of v going to be? So it's the infimum overall possible x1, x2 of L of x1, x2, v, which is f1 of x1 plus f2 of x2 plus v transpose x2 minus v transpose ax1. And the minimization is over all possible x1, x2 in the respective domains.
So is there any constraint on A?
Any constraint on?
A is the PhD.
There's no which AI. No. A can be any matrix. Any matrix. Right. So this is just by definition. I'm just using the definition of the Lagrange dual. Right. Okay. Let me split out the terms which contain x1 and contain x2. This is equal to the infimum over all possible x1 of f1 of x1 minus v transpose ax1 plus infimum over all possible x2 of f2 of x2 plus v transpose x2. So right here I have a linear function in v and x1 minus some function. Can I express this as the conjugate of some particular function? I can write this as the negative of the supremum over all possible x1 of the negative of this particular function. Right? So the infimum of anything can be written as the negative of the supremum of the negative. So this is equal to v transpose ax1, or let me write this as a transpose v transpose x1 minus f1 of x1 minus the supremum of minus v transpose x2 minus f2 of x2. Right, but what is the first term equal to? Minus f1 star of a transpose v. So this is the conjugate of f1 evaluated at a transpose v minus, what is the second term equal to? f2 star of minus v. So the Lagrange dual function can always be expressed as the as a sum of two conjugate functions. And this is true for any constraint optimization problem involving convex functions and convex constraints. Right. So if f1 and f2 are convex, what do we know about f1 star and f2 star? They're always guaranteed to be convex, right? The dual of a function is always convex. So strong duality is it basically amounts to asking whether the minimum overall possible, the maximum overall possible v of this is equal to the minimum of f1 plus f2 of ax. Correct. So in fact, it's possible to give separate sufficient conditions under which the maximization of this particular quantity is equal to the minimum of this particular quantity, or this particular quantity, right? And that is what is called Fenchel duality. Right? So there are certain technical conditions under which these two are the same. I won't go over it in detail, but this gives an explicit connection between the conjugate function and the dual of the Lagrange dual of
Question. So like in like what we started out with, like with just the constraint x belongs to k.
Correct.
We reduced it down to a form where we only needed like this is essentially f2 of x.
Correct.
Like we didn't necessarily need ax.
We didn't
So,
need
like, is ax used in cases where the constraint set might not be convex and you want to transform it, or where do we need like an ax? Where do we need
So,
a?
so this is a more general form. So the question is, how can you formulate it in a more general form? This is only a specific instance. So it's not restricted to solving convex optimization problems per se, but trying to find out when a certain convex function satisfies these duality properties. So generally in Fenchel duality, this problem itself is formulated in a slightly different form. So this is a sum of two convex functions, but you can also express it as a difference between a convex function and a concave function. So it's f1 of x minus f2 of x of ax, right? And you can represent this on the right hand side as the duals, where it's a supremum of a concave function minus a convex function. So that's the most general form in which it is formulated, and then you can study the conditions under which the left hand side is equal to the right hand side. Yes.
Why did we go from two variables x1 and x2 to just a single variable, but matrix multiplication for the second?
So the problem basically involves only one variable. To construct the dual, I wanted to formulate it as a constrained optimization problem. So I introduced this new variable with this particular constraint. So if there was no a, then I would just have set the constraint to be x1 equal to x2. Right? And it's just a trick to express this in terms of the conjugate function.
So initially it was supposed to be like two variables.
No, originally it's a problem. The original problem is a function of one variable. I artificially introduced x2 just so that I could formulate it as a constrained optimization problem. And that led me to bring this new variable v, which were the Lagrange multipliers.
Why is it in particular case more convenient to say formulate it in because essentially if you look at it, they're very similar equations, except the LHS is becoming to function, the RHS is becoming to function.
Correct.
So what is the advantage of?
So, I mean, many of these problems were studied independently under different contexts. We are just connecting the Lagrange dual with Fenchel duality. So Fenchel duality was studied separately. There are other problems where this kind of duality is helpful. But this is a convenient way of representing the Lagrange dual in terms of the Fenchel dual. Now, in many problems of interest, like where you actually want to get a closed form expression, this may not be this may not be something convenient to work with, right? Because fine, I've said that these two problems are equivalent, but in many cases, this is not a function that is easy to work with, right? Because after all, you need to compute the dual of this particular function, and it's not something it's quite unwieldy in many cases, right? But this is just a connection between two very different concepts. All right, any other questions? So far, when I talked about strong duality, I mentioned that at least many of the sufficient conditions, including Fenchel duality, as well as the conditions I mentioned in the previous class, held only for convex functions with convex constraints and some additional properties. But in fact, strong duality can also hold in non-convex optimization problems, although it's difficult to give general conditions under which this holds. So let's see one particular example where this holds, right? All right, so let's look at a quadratic programming problem. Right, so the problem is to minimize x transpose ax plus 2 times b transpose x, subject to the constraint that norm x is less than or equal to 1. When is this guaranteed to be a convex optimization problem? Correct. When A is positive semi-definite, then this is a convex optimization problem. But in general, if A is not positive semi-definite, then this is definitely not a convex optimization problem. But it turns out that this problem always satisfies strong duality, irrespective of the value of A. As long as A is a symmetric matrix, strong duality holds. So let's maybe work out an example. First, let's find the dual of this particular problem. So what is the Lagrangian? There is only one inequality constraint. So this is equal to x transpose ax plus 2b transpose x plus lambda times norm x minus 1. Let me change this slightly. I'll say norm x square is less than or equal to 1. It's the same problem after all. So this becomes norm x square minus 1. This is equal to x transpose ax plus 2b transpose x plus lambda times x transpose x minus 1. I can write this lambda times x transpose x as x transpose lambda I times x. So this is x transpose lambda I x, just so that I can club these two terms together, right? So this is equal to x transpose a plus lambda I x plus 2b transpose x minus lambda. What is the Lagrange dual function equal to? Let's split this into two cases. One where a plus lambda I is positive semi-definite, and the other where it is not. Right? So what distinguishes between these two cases? If a plus lambda I is positive semi-definite, then what can you say about this quantity? What can you say about this quantity? It's always, sorry, it's non-negative, right? So this quantity is always non-negative, and we are trying to take the infimum overall possible x. If a plus lambda I is not positive semi-definite, then what can you say about this? Correct. So there's at least one choice of x for which x transpose a plus lambda I times x is strictly less than 0. Correct? Now what happens if I increase the norm of this x, just scale it up? So it tends to minus infinity, right? So this quantity tends to minus infinity. I can also make this quantity to tend to minus, right? The overall quantity tends to minus infinity, right? So if a plus lambda times I is not positive semi-definite, then the infimum is equal to minus infinity.
It's where the first term is negative, but the second term can be negative.
Again, you can always choose the negative of that particular x, right? So if b transpose x is positive, then you can take minus x. It does not affect the first term. So you can choose an x for which the second term is negative, the first term is also negative, and you let the norm of x to tend to infinity. So the infimum overall possible x of this particular function is equal to minus infinity if a plus lambda I is not positive semi-definite. Okay. If a plus lambda I is positive semi-definite, then what can you say about this function? It's convex. So you can find the infimum by just finding the stationary point of this function. What is that equal to? Yep. So set the gradient to be equal to 0. What is the gradient equal to? It's the gradient of x transpose a plus lambda I x plus 2b transpose x minus lambda. The gradient is taken with respect to x. So it is 2 times a plus lambda I times x plus 2b. Set this to be equal to 0. So what should x be equal to?
Lambda is equal.
Sure, the inverse need not always exist, so it's going to be the pseudo inverse.
So this is APSD.
Yeah,
This is PSD, right?
correct, but A need not be a square matrix, right? So A plus lambda I is PSD, A is not, A need not. So x is equal to A plus lambda I, the pseudo inverse of this, times B.
So how can A not be square?
Sorry?
A has to be
A plus
square,
lambda
right?
I special.
Ah, sorry, yes,
You need to do
asymmetric, agree. So, but
But it still have a 0 again.
it can still have a 0 again. So A need not be full rank, or A plus lambda I need not be full rank. Okay, so what is this equal to? This quantity equal to? Can you plug this into this and let me know?
So is it always so?
Why not?
Suppose
Yeah,
A is not full rank.
A is a full rank matrix. Okay.
Let's see.
Okay. So what is the infimum equal to? What is the Lagrange dual function equal to? Minus
Minus A plus lambda minus of x. No, it's over.
are you sure? Because there should be an x transpose A plus lambda I x. X equal to minus A plus lambda I pseudo inverse B. The formula for score is like A transpose A whole inverse times A transpose. So if I compute it, like use A plus lambda inverse, like I'm getting A plus lambda inverse. A plus lambda inverse. Sure. I mean, yeah, in this case, it's still going to be the inverse. Fine, we can just take the inverse, I guess, in this particular case. A is, I forgot that A is square.
B
Yeah.
transpose, the negative of B transpose, the super inverse times B.
So it is negative of B transpose A plus lambda I inverse B transpose minus lambda.
Or just B.
Ah, sorry. Minus lambda. Okay, so what is the dual optimization problem?
Lambda greater than equal to 0 implies A plus lambda will also be.
No, it's not sufficient. Right? Minus lambda subject to lambda greater than or equal to 0 and A plus lambda I is positive semi-definite.
Could there be a case where lambda greater than equal to 0 implies A plus lambda will not be there?
Lambda greater than or equal to 0. Well, for example, if, okay, let's take an example. Yeah. So let's take one specific example. Take A equal to 2 minus 1. All right. Now, if we look at A plus lambda I, this is 2 plus lambda 0 lambda times I is equal to 2 plus lambda 0 0 lambda minus 1. Now, lambda greater than or equal to 0 does not imply that A plus lambda I is PSD, right? And just because A is, okay, so this is maybe, yeah, so if A was PSD originally, then you can choose a lambda less than 0 for which A plus lambda I is PSD. So these two constraints are, one does not necessarily imply the other in general.
Alternatively, if you find some lambda for which A plus lambda is PSD,
Yes.
we can just increase the lambda's value, right?
You can increase
Lambdas.
the range of lambda, you mean?
We can use some lambda prime which is greater than lambda. satisfy that.
I'm not sure what.
So let's say I found a lambda 1, so I start taking lambda I is greater than.
Fine.
If I choose a lambda 2,
Yes.
which is greater than lambda 1,
Yes.
will it also satisfy that?
Sure.
It would.
It would.
Then there won't be the contradictory condition.
No. There's no contradiction. But you need both. The only point I'm trying to make is that you need both these constraints, because lambda greater than or equal to 0 is, so for example, just having a plus lambda I to be PSD would of course make this a convex optimization problem, but the optimum value may not be a lower bound on the primal problem, right? Because you also need this additional constraint that lambda is greater than or equal to 0. It's only then that d star is less than or equal to p star. Okay, so let's take this example itself and try to find both the optimum, the primal and the dual solutions. What is f of x equal to? The primal problem. Okay, let's also take b to be equal to half, 1/3 or something. So it's x transpose ax plus 2b transpose x. So this is equal to, so it's 2x1 square plus minus x2 square plus 2 times half times x1, which is x1 plus 2 by 3 x2, subject to the constraint that x1 square plus x2 square is less than or equal to 1, right? This is non-convex. Let's find the dual. What is g of lambda?
So is it possible to equal to constraint?
I'm sorry?
Is it satisfies with the equal to constant also? Let's say
Which one?
mod of ax equal to some constant.
So you're saying that x1 square plus x2 square equal to 1?
Some mod of some ax equal to 0
Sure.
satisfies.
Yeah. So are you saying that if strong duality is satisfied if I have an additional equality constraint?
No, instead of this inequality constraint,
Yes.
let's say mod of bx equal
Okay.
to 0.
Okay.
Is it satisfied of these properties of strong duality?
So strong duality is okay.
Instead of inequality, equality.
I guess it is satisfied. I'm not sure. Yeah, so in general for non-convex optimization problems, it's difficult to say if it's satisfied or not. minus lambda
This is a plus lambda or a plus lambda equals.
it's inverse. What is this equal to? Minus 1 over 4 times 1 over 2 plus lambda 1 over 9 times lambda minus 1 minus lambda. Right? And subject to what constraints? So when is a plus lambda I positive semi-definite?
After the one. So
Yeah, we can redefine this to be plus infinity when lambda is equal to 1. But otherwise, yeah, strictly speaking, lambda should be greater than.
it's just become negative infinity, so it doesn't matter.
Well, its function is not defined for lambda equal to 1. So it's set to minus infinity when lambda equal to 1, and it is equal to this when lambda is strictly greater than. Right? So let's try to maybe numerically evaluate this. It doesn't seem like it's easy to solve. So let's try to visualize both the primal function as well as the dual function. X1 and X2. So I'm only interested in the region where x1 square plus x2 square is less than or equal to 1, right? It's a constrained optimization problem. So let me try to visualize the function only in that particular region. So I'll set for all regions, for all points for which x1 square plus x2 square is greater than 1, I'll just set it to plus infinity or not a number. So So this is what the function looks like. It's basically a saddle, right? And where is this function minimized? Minimized at one of these points. We want the minimum of this. So it's a non-convex, it's clearly a non-convex optimization problem. Let me try to numerically find out what is the minimum. Let me set this to infinity instead. So the minimum value is minus 1.74, right? Now, let me say L is, so I want to plot this function in the range lambda greater than or equal to 1. Then G is 0.25 by 2 plus lambda minus 1 by 9 minus lambda. Alright, so this is what the dual function would be. It's concave, right? I mean, as the dual function is always guaranteed to be concave, the maximum value is still roughly the same, 1.74 something. So this is an example where you have a non-convex optimization problem. The dual function is a convex optimization problem. So we started with a non-convex optimization problem, but then we could convert that to a convex optimization problem and then use convex optimization techniques. So in scenarios where you know strong duality holds, you can convert your non-convex optimization problem to a convex optimization problem using duality. If you don't know whether strong duality holds or not, you at least have the guarantee of weak duality. So even if you do not get the exact solution, you can still get a certificate. You can get a lower bound on the optimum value of your original non-convex problem using convex optimization techniques.
So here the target A is symmetrical because we are able to construct some matrix lambda.
Yes. Otherwise, that's not. Yeah. All right. Any questions? Okay, so let's look at the dual for a couple of other problems. Suppose that I have what I call a standard form linear program. So the goal is to minimize C transpose X subject to the constraints that A times X equal to say B and X is greater than or equal to 0 component wise. The Lagrangian V is equal to C transpose X plus lambda times X plus V transpose AX minus B. So the lambda corresponds to inequality constraints and the V corresponds to equality constraints.
Minus lambda.
I'm sorry? It's minus lambda X. Yeah. So I can also write this as, yeah, it should be lambda transpose X. So this is the infimum C transpose X, or yeah, let me write this as X transpose times A transpose minus A transpose V minus lambda plus C, and what remains? Minus V transpose. What can you say about the infimum? Okay, for all lambda and V,
C minus if the quantity is negative,
which quantity is negative?
or rather it has negative component.
Okay, so can you again?
This is a case where
All right. So for any fixed lambda and V, this term is always a constant, right? So we're really interested in finding out what the minimum of this function is. Now, if A transpose V minus lambda plus C equal to 0, then what is the infimum equal to? It's equal to minus V transpose B. So it's minus V transpose B if A transpose V minus lambda plus C equal to the 0 vector. If this is a non-zero, then what can you say about the infimum over all possible x? Should be minus infinity, right? Right, because it's a linear function. Okay, so what can you say about the maximum of g of lambda comma v? Or in other words, the dual program is to maximize minus v transpose b subject to lambda greater than or equal to 0 and A transpose V minus lambda plus C equal to 0. We can reduce this to a single constraint because, well, A transpose my plus C minus should be equal to lambda, which has to be greater than or equal to 0. So this is the same as maximizing minus V transpose B subject to the constraint that A transpose V plus C is greater than or equal to 0. So this is called the dual linear program. And it's known that for every linear program, strong duality always holds. So at times you may want to look at the dual linear program instead of the primal program itself, because potentially it could involve fewer variables or fewer constraints. All right, so let's, any questions? So let's look at another problem of entropy maximization. So given any probability mass function, let's call it P, P. So this is over, let us say, the set 1, 2, 3 up to n. Right? It's a probability mass function over some finite set. Let's just label this as 1, 2, 3 up to n. The entropy of P is defined to be summation I equal to 1 to n pi log 1 over pi. Right? And when I say pi log 1 over pi, when we have pi equal to 0 for some I, then we say that pi log 1 over pi equal to 0. That's how we are defining this x log x function. So in many problems, particularly information theory, you want to find the PMF that maximizes the entropy, subject to a bunch of constraints. So goal is maximize, or let me formulate it as a convex optimization problem. So minimize minus h of p h of p subject to some constraints on the PMF. And typically these constraints are expressed in terms of moments of the random variable in question. But as we've seen a little bit earlier in a previous class, any moment, how does it behave with respect to the PMF in question? Is it linear, quadratic? Is it a convex function? It's always linear, right? So every moment on any PMF or PDF for that matter is linear in the PMF, is linear in the distribution, right? So I can express this minimization, whatever, maximization of entropy with respect to moment constraints as a minimization of the negative entropy subject to some linear inequality constraints, such that A times P is less than or equal to some B. Right? I could also have extra equality constraints, but fine, let's just assume that there are only inequality constraints for now. Right? If you want, let's pick a specific problem where I want to minimize minus h of p, where p equals p1, p2, p3, subject to some constraints. Let's say that p1 plus 2p2 plus 3p3 is less than or equal to, say, 0.5. And of course, you also have the constraint that p1 plus p2 plus p3 equals 1, because after all, this has to be a valid PMF. So firstly, is this a convex optimization problem? X log x is convex.
So we also need an explicit constraint for non-negative effect.
Yes. If p greater than or equal to.
How it will be less than 0.5?
Sorry? No, I'm imposing this additional constraint that the mean is less than or equal to 0.5. Sorry. Let's say 1 point. 1 point. So x log x is convex. So this is a convex optimization problem. Let me try to construct the Lagrangian first. V equals pi log pi plus lambda 1 times minus p. I have a non-negativity constraint plus lambda 2 times, say, generally, this is going to be AP minus B plus V times P1 plus P2 plus P3 minus 1. So what would be the Lagrange dual? So what can you say about this function, the Lagrangian as a function of P? It is convex, right? So what's the stationary part?
this case, P1 plus P2 is always equal to that part A.
Sorry, which one?
P times
Correct.
that would be lambda plus that lambda 1 times of P plus lambda 2 times of A minus P goes to minus
So you can choose that. You can choose P1, P2, P3.
but that lambda plus lambda A goes to minus.
Why can you always choose that? Okay.
Lambda 1 plus lambda 1 can be minus.
For any choice of lambda. I agree that when you take the infimum, there are some values of lambda for which this becomes minus infinity. The infimum is equal to minus infinity. But is it true for all lambda? There are some values of lambda for which the infimum is finite. So really this should have been lambda 1 transpose. The first constraint is P. So we can assume that this is the natural logarithm for now. The infimum. So we want the infimum, but we can do that in perhaps two steps. So firstly, when is this finite? When is the infimum finite? And when is it going to be minus? When this function is defined for infinity, for pi greater than or equal to 0 for all I. So the first function is always non-negative. Sorry, it's always non-positive. So as pi tends to infinity, what happens to this particular quantity? X log x. It tends to plus infinity. As pi tends to 0, what happens to it? Tends to 0, right? And in between increases. Correct. Yeah, so it will decrease and then increase. It's not monotonically increasing in the pi, right? Okay, so good. So whatever happens, it's always bounded, right? For all, so if you fix a maximum value for all the pi's, this function is going to be bounded. So it's bounded from below. right? It doesn't tend to minus infinity as PIs tend to infinity. Okay, what about the other terms? So the remaining part is linear, right? So as the PIs tend to infinity, so there could be a choice of, there could be a particular way of choosing P for which this quantity tends to minus infinity. Will that happen? And if so, when? Okay, maybe let's stop here and continue in the next class. But that's a homework to find out the behavior of this particular function. Is there some value of P for which this becomes minus infinity?
The specific case or specific case of A, in this particular case, whatever value you take for say P, like next, right? AP will be growing at a faster rate.
AP will be growing at a faster rate than what?
Then
Okay.
minus P.
Okay.
So like always
Okay. But then remember, you also have this quantity over here which tends to plus infinity.
We can't go
not here.
P is so P is greater than or equal to 0. Let's say.